Okay, let's continue with application of Ritter's lemma to the pricing of European financial claims. Okay, first, let's start with a simple exercise. Let's be a little bit more abstract. Let's recall that if you have some random variable z, that is normal, standard normal random variable, and we have a CDF of z cumulative distribution function. That's basically just the probability that z is less than t. So this CDF looks like this. Yeah. And this is t, this is f of t. F of 0 is the probability that our random variable is less than 0. It's just 1/2 by symmetry. Okay, and my simple question is the probability that, let's say, W7 will be, or maybe to simplify calculations, W16 will be bigger than 2 in terms of this CDF of a standard normal. So that's an easy exercise, just warm up to what we will do in a few minutes. Just a warm up. How can we do this exercise? Okay. We just recall that W16 has normal distribution with mean 0. W16 has a normal distribution with mean 0 and variance 16. So to standardize this random variable, we need to subtract expected value and divide by square root of variance. So that's a standardization procedure. And now we have a random variable that is normal 0, 1. And hence my question, probability that W16 is bigger than 2, can be restated in terms of standard normal random variable, like W16 minus 0 divided by square root of 16 is bigger than 2 minus 0 divided by square root of 16. Hence, that's 1 minus probability that my standard normal random variable will be less than 2 minus 0 square root of 16. And that's just basically 1 minus CDF, cumulative distribution function, evaluated at the point 2 over 4, 1 minus f of 0.5. And let's recap the basic property of CDF of a standard normal. If you need to calculate the probability that this is a probability that standard normal is less than or equal to t, and obviously you may restate this like, so this is t, let t be positive for simplicity. And if I just calculate the minus t point and minus t point, and I clearly see that by symmetry, probability that standard normal is less than t is equal to probability that standard normal is bigger than minus t, and hence f of t is equal to 1 minus f of minus t. So we may always rewrite the expression 1 minus f of 0.5 like f of minus 0.5. That's the same thing. That's just the symmetry of a cumulative distribution function. Okay, so we are done with our first exercise. Now let's continue. Now let's consider the Wiener process with drift. Let's consider exercise 2, my exercise 2. I have WT, that's a Wiener process. And I will add a small drift. Let's say that WT star is WT plus, let's say 0.5 times T. And I may ask a similar question: what is the probability that drifted with that Wiener process with drift? So that's a Wiener process with drift. Yeah, that part that I add is the drift. Yeah, and I may ask a similar question: whether the probability that Wiener process with drift at time, let's say 25, will be bigger than I don't care 10. And the solution basically is similar, but we see that my first question is find this probability, and the second question is WT star a standard Wiener process. So I have two questions. Is WT star a standard Wiener process? And the first question is the answer to the second question is no, yeah, because if I calculate the expected value of WT star, I will get the expected value of WT plus 0.5T, and I see that is 0 plus 0.5T, and WT has a normal distribution with mean 0.5T and variance T, and the standard Wiener process WT, it should have a normal distribution with mean 0 and variance T. So WT star is not a standard Wiener process.
Shouldn't every Wiener process have a mean of 0?
Yes, we have assumptions that standard Wiener process. We have the following assumptions for standard Wiener process. There are 4 assumptions. W0 is 0. Second assumption that WT minus WS for standard Wiener process has normal distribution with mean 0 and variance T minus S. We say that increments are independent. Increments are independent. And trajectories are continuous. Trajectories are continuous with probability 1. Continuous with probability 1. Probability 1. So assumptions, and this assumption is violated for WT star. Yeah, that is not satisfied. if we speak about assumptions for standard winner process. You may say that it's a winner process with drift. That's okay to say that's a modified winner process. Okay, that's winner process with drift, but that's not a standard winner process. I mean WT star. WT is a standard winner process. The standard. Okay, and what about probability? Basically the same thing. Probability that WT star is bigger than, sorry, W25 is bigger than, I don't know, 10. I standardize, I subtract how much should I subtract? I should subtract this quantity. So I subtract 25 over 2. I divide by variance, sorry, by square root of variance. I will get 10 minus 25 over 2. I divide by square root of variance. I will go to standard normal distribution is bigger than 10 minus 12.5 is minus 2.5. So over 5, that's the probability that normal standard distribution will be bigger than minus 1 over 2. And hence, that's just 1. So that's 1 minus probability that, so, and standard normal distribution is just 1 minus CDF at minus 1 over 2, and that is just 1 minus CDF at 1 over 2. That's the CDF at 1 over 2. Okay, we have solved the problem. Now let's move on. We have a very strange theorem. It's a little bit abstract. It's hard to understand, but we will try. It's called Gersonov theorem. And it says, imagine WT is a standard winner process with respect to probability P. With respect to probability P. And imagine that WT star is a drifted version of this winner process. So it's WT plus some alpha times T. So we have a drift. And Gersonov theorem says that if we have a standard winner process and the modified process, then we may introduce a new probability P star such that WT star is a standard winner process with respect to P star. That's a little bit strange. What does it mean? Because normally when you study probability theory, you have only one probability. And when you calculate probability of some events or you calculate some expected value, you don't specify, you have only one probability. But this Gersonov theorem, the level of abstraction is a little bit higher. So in this theorem, you have two different probabilities. So that means basically, imagine a, so what does it mean, two probabilities? So imagine that you have a random variable, let's say R, that has two values, -1 and 1. And one guy believes in probability P, and he believes that probabilities are 0.2 and 0.8. And the other guy believes in probability P star, and he believes that the probability of -1 is, let's say, 0.6, and probability of 1 is 0.4. And if you have two probabilities, then basically you, for all questions about characteristics of random variable, you will have two answers. One answer calculated with P, and other answer calculated with P star. Yeah. For example, what are the probabilities that R is equal to 1? Oh, it's 0.8. What is the probability star that R is equal to 1? Oh, that's 0.4. Yeah. What is the expected value of R? Ah, you have two expected value now. The expected value with calculated with respect to P, and expected value calculated with respect to P star. Yeah. And all probability characteristics have two versions now. The expected value ordinary, non-starred, yeah, is 0.8 minus 0.2, that will be positive, that will be 0.6. The expected value star is 0.4 minus 0.6 is minus 0.2, yeah. And the law of distribution is different, yeah. If we can say that, for example, so okay, you can calculate variance so far. You can calculate variance star of R. Yeah, all characteristics.
Sorry.
You have two versions. Yeah.
Can I ask a question?
Yeah.
What does it mean that some Wiener process is a standard Wiener process with respect to some probability? Like with respect to some probability, seems can't understand it.
Okay, let's understand this example first. Yeah, you have two different ways to calculate expected values and variances and probabilities. Okay, you have two ways. Yeah, that's clear. You have one random variable, but you have ways to calculate its characteristics under P and under P star. You have different expected value, different variances. Okay, yeah, that's clear. Okay.
Yeah.
Okay, now let's imagine the other case. You have the random variable R that has values 0, 1, and 2. And P, you have two probabilities, P and P star. Under P, you have probabilities 1/4, 1/2, 1/4. And under P star, you have probabilities, let's say, 1/3, 1/3, 1. And that's correct to say that R has a binomial distribution with n equal to 2, and the probability of success 1/2. Yeah. If but R under the probability star, R is not binomially distributed with n equal to 2 and probability 1/2. Yeah. If we speak, if we use this probability, yeah, that's binomial distribution. Okay, you recognize binomial distribution. If we have a fair coin, we throw it twice. What is the probability that we will observe two heads? We will observe two heads with probability 1/4. We will observe 0 heads with probability 1/4. With one head with probability 1/2. But if I calculate probabilities with star version, then it is not binomial. Yeah, it has other distribution. it is equiprobable. Yeah, it has equal probabilities. That's okay. Yeah, the law of distribution depends on the probability. Okay, under one probability you have one distribution. Under second probability star, you have another distribution. That's okay.
Okay, but this random variable, it's not a process.
Yes. And now let's go back to this theory. What does it mean that WT is a winner process with respect to probability P? That means basically that if you consider any two random variables WT and WS, then under probability P, they will be normally distributed with mean 0 and variance T minus S. Yeah, that's the assumption of the winner process. Okay? So what does it mean? Winner process is a standard winner process with respect to probability. That means when you calculate the distribution using probability P, you will observe a normal distribution 0 T minus S. Okay? That's the assumption of a standard winner process. Yeah? That's clear?
Yes.
Okay. Now let's calculate the same, the difference of WT star minus WS star. Basically, that should be WT minus WS plus alpha T minus S. So this distribution, if I use probability P, that should be normal. Yeah. What is the distribution of this if I use P as my probability? Yeah. If I use P, then this difference will have under P the normal distribution with mean alpha T minus S and variance T minus S. That's okay?
What does it exactly mean to use probability P on a winner process?
Sorry?
What does it exactly mean to use probability P on a process?
You may calculate probability. You have two different ways to calculate probability. And there are two guys. One guy say, oh, probability that W5, okay, let's, so you have two opinions. One guy thinks that probability that W5 is bigger than 0 is 1/2. And the other thing, no, probability P star that I use, that W5 is bigger than 0 is 2/3. You have two probabilities. One guy calculates probability in one way, other guy calculates probabilities the other way. You have two probabilities. Random process is just a collection of random variables. Yeah, what does it mean? A random process. Random process is just many random variables. What does it mean? I have a winner process. I have W1, I have W2, I have W3.5, I have W7, I have W10.2, and so on. So basically, there are a lot of random variables. A random process is just a bunch, a big pack of random variables. What is a random process? Just a collection of random variables. And there are two guys. One calculates probabilities using his way, P way, and the other guy calculates probabilities using his way, his own P star way. Okay? And maybe the true probabilities are the P star star way. Okay, maybe these two guys are both wrong. I do not claim that one of them is right. I just say I have two ways to calculate probabilities. That example shows the idea with one random variable, but a random process is just a big pack, a big set of random variables. Okay?
Okay, so we have like some rules. That's our estimated probabilities, and after when we get like our how to say it, like when we estimate what winner process is equal to at some step, these estimations are some random variables that are normally distributed. So that is what is actually meant by like a standard winner process with respect to probability P. Am I right?
Sorry, we estimate nothing. Estimation is from mathematical statistics. We know. We do not estimate. Estimate is a bad word. Just we have two probabilities. One guy calculates probabilities one way, the other guy calculates probabilities the other way. That's all. Point.
So we don't calculate values of winner process, we just calculate like probabilities.
We are not calculating, so we're calculating probabilities. Okay, let's provide a specific example. Maybe it will be better. Okay. Okay, let's consider the exercise. WT is a winner process with respect to P, and WT star equal to WT plus, let's say, 1T is a winner process with respect to P star. Okay, there are two probabilities, P and P star. And my question one, calculate probability that W1 will be bigger than 0. Calculate probability that W1 star will be bigger than 0. And point B, calculate probability star that W1 will be bigger than 0. And calculate probability star that W1 star will be bigger than 0. Calculate these probabilities. Okay, by the definition of my process WT, that's a winner process with respect to probability P, yeah? With respect to probability P. Okay, this is a probability that W1 is bigger than 0. What is the answer?
Maybe 0.5.
Exactly, that's 0.5. Because I said that WT is winner process. So W1 has normal distribution. If I use probability P, it has normal distribution with mean 0 and variance 1. Okay. Now, what about probability that W1 star is bigger than 0? But they are linked in this way. So that's probability that W1 plus 1 is bigger than 0. So that's probability that W1 is bigger than minus 1. So that's probability that by symmetry, yeah, that's probability that W1 is less than 1. That's the CDF evaluated at 1. If we use tables of standard normal distribution, or we just use computer to calculate this CDF. If we will do this, we will get something like, just a second, 0.84. So you can just use tables of normal distribution or just use computer to calculate this probability. That's okay?
Yes, it's perfectly clear. Like, no, it doesn't actually feels like some abstract theorem. We just say that we have some winner process, and then we have a modification of this winner process, and well, it feels almost obvious that we will have different probability functions for these two winner processes.
No, that's really magic. That's, for example, so no. That's a very hard theorem. That's not really obvious. It says basically that for any constant alpha, it's possible to introduce this probability measure. To show you some examples that you can't always, okay, let's imagine the following example. Let's imagine that you have X that has values 2 and 5, yeah? Or maybe something like 0 and 1, probability 1 over 2, probability 1 over 2. That's more or less obvious that X under probability P has binomial distribution with n equal to 1 and probability 1/2. And that's expected value of x under probability p is 1/2, okay? That's fine? And my question, can you create probability measure p star that expected value of x is equal to -10? Can you create such a probability? The obvious answer is no. Yeah, you can't create such a probability. Yeah, because you are free to introduce anything you like. You will never obtain the probability, the expected value -10. That's okay. And if we go back to our example of Gersonov theorem, if I calculate expected value under P of W star 10, obviously it will be 10, yeah, because the expected value of this guy is 0. This is 10, so expected value of this guy is 10. And Gersonov theorem says that, oh, you may introduce, so it asserts that there is a probability measure P star such that expected value start with, so expected value with respect to P star for WT star is 0. So you can drop expected value by 10 by changing probability, yeah? So it says a lot. You can adjust, and you have not one random variable for Gersonov theorem, you have infinite collection of random variables. And Gersonov theorem says that you may change probability in such a way to make all expected values as you need, all variance as you need, all probabilities as you need to have a normal distribution with corresponding expected value and variance. That's not obvious, because there are many restrictions. For example, in this case, you can't even change, you can't drop the expected value of this random variable even by 2 by changing probability, because of the small number of values. You are bound that you can't change the expected value by 1. And in Gersonov theorem, it says, oh, you can adjust by changing the probability, you can adjust all expected values, all probabilities, all variances, all covariances, yeah? Because if you calculate covariance of something with something, so you need to adjust everything, yeah? So that's not obvious. You have a lot of limitations when you adjust only probabilities, yeah? That's okay? For example, if I consider the slight modification, let's consider WT A that is equal to WT squared, then obviously you can't create a probability measure PA such that WTA is a winner process. So this can't be, this is not, this can't be a standard, winner process under PA. Yeah, it is always non-negative. Yeah, always non-negative. Even you change the probability in a fantastic way, you will never obtain probability 1, 2 for negative values of WTA. Yeah, so that's not really an obvious theorem. You have a lot of
how does the change of probability translate to a continuous case? Like, for example, if we would try to compare it with normal distribution, like I don't know, maybe PDF, how can we transformate it? Like, what I want to say is which transformations of P to P star are permitted and which are prohibited?
Yeah, that's very difficult. That's a good question. That's tough. It's not obvious. This example shows that you can't. Yeah, that's a tough question. So we will not go into the proof of the Gersanov theorem. Yeah, that's tough. So Gersanov theorem asserts that if you add a drift in the Wiener process, you can correct the drift by correcting probability. That's great. So that's not obvious. So even the question how we describe probability in continuous way, even this question is difficult. Okay, let's go on. So that's a very interesting question, but the answer is difficult. Okay.
Can I ask the last question? I think it's easy. Does this theorem also guarantees that we always can deterministically find this new probability P star?
Yes, there are some ways to describe this probability measure using some more advanced techniques like Redon-Nikodym derivative. Yes, there is a special way to describe this probability, but that's a way a little. So is there a way to describe this probability? Yes, there is a way to describe this probability. The change of probability itself is deterministic, yeah, by knowing the probability of so yes, the change of probability is a well-defined process, yes, but that's outside the scope. The problem with stochastic calculus that it's very mathematically intensive and the one step, so we are like in a so that's a very dangerous water. So we follow a very narrow path to some great results, and one step to the left, one step to the right, you are lost. Or basically we need a lot of time to go through all the details. So basically, yes, the answer is yes, but we won't consider this process of creation of P star. We just believe, okay, there is a P star. Okay, we believe that it exists.
Thank you very much for this profound explanation. By the way, once again, how is the derivative called?
Redon-Nikodym. I'm not sure that it's like this Nikodym. Let me check. Let me Google. I'm not sure in the spelling of the name. I know how to write it in Russian, but I'm not sure that it's. Just a moment, I will tell you. Okay, so let's continue with our, and it will Google. Okay, no, I'm wrong. That's I here and Y there. Redon-Nikodym.
Thank you very much.
So that's describe the process how to get from P to P star. Okay, let's see how this, why do we need this process? Okay, let's consider the Black-Scholes model. In the Black-Scholes model, the price ST is given by the process S0 times exponent of mu t times exponent of sigma WT minus sigma squared over 2 times t. So that's the behavior of a share price in the Black-Scholes model. Okay, Now let's consider the discount share price. We have so in Black-Scholes model, now we have the price of a share that is positive. It starts at 0, it fluctuates, it can't be negative. We have exponents. So that's a more or less realistic assumption about the share price. This process is a martingale. That's a martingale. That's a martingale. And this is the growth rate built in the Black-Scholes model. Okay, and let's consider the discounted share price. We have R, the risk-free interest rate. We have risk-free interest rate R. And if I consider the discounted share price, so that's the share price process, share price. And if I consider discounted share price, so let's say MT is ST divided by exponent of RT. So let's check, let's solve the following exercise. Is MT a martingale? Is MT a martingale? Yeah, is MT a martingale? Okay, how can we check that something is a martingale using our powerful tools like it is lemma? Okay, let's copy all we need. Let's copy all we need. And MT is exponent minus RT times ST. And first exercise is to check whether MT martingale. We have a very powerful tool to check. We just apply it as lemma. The answer is calculate DMT. If DMT has a form of something times DWT, then yes, it's a martingale. If it has the form something times DWT plus something times DT, then the answer is no. Yeah, we have an easy way to check whether something is a martingale. Okay, let's calculate DMT. Let's calculate DMT. I remind the expression for Ito's lemma. Yeah, if MT is a function, some function of WT and T, that's the case in the Black-Scholes model, then DMT is equal to H prime with respect to W times DWT plus H prime with respect to T times DT plus 1/2 H prime prime with respect to WW times DT. That's the Ito's lemma. Ito's lemma. Okay, let's check whether our discounted share price process is a martingale. Okay, let's write ST the following way. That says 0 times the exponent of mu minus sigma squared over 2 times T plus sigma W. Okay, so if I calculate MT, that is discounted share price process, I just write minus RT times ST. I will get S0 times exponent mu minus R minus sigma squared over 2 times T plus sigma WT. And if I calculate DMT, what will I get? Let's calculate this. Yeah. First, the derivative with respect to W. The derivative with respect to W is just sigma times all these big stuff. Yeah. Exponent of mu minus r minus sigma square root of 2 times t plus sigma wt times dwt. Plus, the second term I need is, so I calculate these three terms. Yeah, the first one is calculated. Now let's go to the second one, the derivative with respect to t. I will get, by the chain rule, I will get mu minus r minus sigma squared over 2 times O times this S0 times exponent mu minus r minus sigma squared over 2 times t plus sigma wt times dt. Plus, now the third term, 1 over 2 sigma squared S0 times exponent mu minus r minus sigma squared over 2 times t plus sigma wt times dt. Okay, I've calculated all three terms in the dm shorthand notation. I recap that that's just a shorthand notation. If I'd like to recover the full form, then I need to add the integrals everywhere. So just recap that that's a short notation. Okay, let's cancel the term that we can cancel. This guy and this guy, they will cancel out. Okay, what can we write for DMT? We can write DMT in the following form. It just it is just ST times, so this is ST, yeah? This is ST, that is ST, that is ST. So let's take out sigma times ST. What do we'll get inside brackets? We will get dWt plus mu minus r over sigma times dt. Okay, let's look at this expression. And we see that we have calculated DMT. We have the dt term that is non-zero in general. Yeah, if mu is bigger than r, and in real life, if you have free risk rate r, then you will never buy something that is risky and has the same mu. So in real life, mu is bigger than r. Yeah, mu is a growth rate of a risky asset. R is a growth rate of a riskless bond. So this term is non-zero. Yeah, and hence we have the second case. Yeah, we have something before dt. And hence, this is not zero, and hence MT is not a martingale. And basically, that means that it's not easy to calculate expected values. And now we have a brave Gersanov who says, I will save you. I will create another probability measure that will allow you to calculate all expected values in a like a charm, like magic. So you will just, so this is Gersanov. brave Gersanov, brave Gersanov. He says, okay, let's consider WT star, that is WT plus mu minus R over sigma times T. And Gersanov says that, oh, I proved the theorem that there is a probability P star. Okay, and under probability P star, probability P star, WT star is a standard Wiener process. Standard Wiener process. Okay, what does it mean? It means that under P star, we can say that DMT. Okay. We we apply Ita's lemma once more to this expression. We calculate dWt star. Once again, I use Ita's lemma. Yeah. I calculate the derivative with respect to W times dW, the derivative with respect to H times, with respect to T times dt, plus the second derivative with respect to W. In this case, I will have the derivative with respect to W, it's 1 times dW, plus derivative with respect to T is mu minus R over sigma times D, plus the second derivative with respect to W, that will be 1 over 2 times 0 dt. Hence, I see that dMT can be replaced by sigma times ST times dWt. And hence, there are no dt term, no dt, and hence MT is a martingale, under probability measure P. Now we have a complete so it seems that we have we have created a new probability measure. We don't know how to calculate, we don't know even how to write it, but this probability measure makes MT a martingale. So the moral of the story, okay, it seems that we have something useless. Yeah, it seems. What do we have at this point of time? We have under probability P star, MT, the discounted share price, exponent minus RT ST is a martingale. Okay, now let's check the bond price. ST is a share price. Now let's calculate the discount. So the discounted bond price, BT, the riskless bond price. So our BT evolution is B0 times exponent RT. So our riskless bond evolves like this. We have B0, this is T, we have BT, the price of a riskless bond. Okay, the share is risky, so that's a share as 0. Oops, it may go down, I don't know. BT is riskless bond. If I consider the discounted bond price, so if I consider discounted bond price, what do I get? I get exponent minus RT times BT. Obviously, I will get B0. The discounted bond price is constant. And the discounted bond price is constant. This is discounted share price. Discounted share price. And this is T. This is MT equal to exponent minus RT times ST. And the discounted share price, we know that under P star, that's a martingale. And that's a constant. And with constant, that's easy. When you change probability measure, if you have something that is equal to 2 and non-random, you may change probability measure in any way you like. If something is constant and non-random, you may change the probability measure, but it will be constant and non-random. Yeah. If you have something that is constant in time, okay, you may do nothing. So that under P star, that's a constant under P star. Okay. Now, the moral of the story. Imagine that you have a very, very complicated trading strategy. So now imagine that you have a complicated trading strategy XT. XT, a tricky trading strategy. You at different moment of time you trade this share and you trade this bond. Tricky trading strategy. You trade. So we trade the share and the bond.
Sorry, could you please explain the connection between share dynamics and bond dynamics in this example? So I didn't really get how from one formula we got the bond dynamics and the share dynamics.
Yes, the bond dynamics is very simple. It's riskless bond. It just the prices goes up. You buy one share and you wait. After 1 year, it will be multiplied by exponent R. After 2 years, your welfare will be multiplied by exponent 2R and so on. So that's a bond dynamic. It's very simple. And the share price, this formula related to winner process, you may lose almost everything after 1 year if WT is very negative, and you may gain a lot.
That formula is the classic Black-Scholes model, right?
Yes.
Oh, thank you very much.
These two formulas are, but they are assumptions in many models, not only in the classic Black-Scholes. So that's a riskless bond. It should be riskless. So there are many extensions, like you may have dividends. So there are other models for the bond price. The riskless rate may be. So you may introduce stochastic interest rate models. So that's not the only possible model for the bond price, but that's the simplest one. The simplest one, the assumptions in the Black-Scholes. Yeah, there may be other assumptions. Okay, let's continue. So we have a tricky trading strategy. We trade the share and the bond price. So we buy 5 shares and sell 7 bonds to cover expenses. After 1 month, we buy 1 more share and we sell the necessary number of bonds and so on. So we consider some trading strategy, but because we are trading the share and the bond, we do not. We have no third. So we consider the Black-Scholes world when we have only 2 underlying assets, the bond and the share. So there are no other shares in our world, Black-Scholes, we have only one share. So that's a simple model. But all prices are martingale. The discounted price of a bond is a constant. The discounted share price is a martingale. Hence is basically XT is a combination. We combine, we trade. We may do transactions any moment of time we wish, but basically exponent of minus RT XT is a martingale, because we trade, we have two assets to trade. The bond price and the discounted bond price is constant, and discounted share price is a martingale. Okay, then exponent minus RT XT is a martingale under P star. Hence, and that's the fact that we will use X for a martingale. The expected value X0, the expected value does not change for martingales. So X0 should be the expected value star of exponent minus RT times XT for all T. So that's great. And that's a fact about the real world. So to calculate current price of any trading strategy, of any tricky trading strategy in the Black-Scholes world, you just need to calculate expected value. Okay, what does it mean for our applications? Okay, let's consider some particular examples. Let's solve the following problem. Okay, imagine that my tricky trading strategy, I have organized a tricky trading strategy that basically, here is time 0, we are at 0. After 1 year, I promise you to pay, for example, I will pay you, you will receive $1 if as T is twice as big as 0. I pay you $1 if the final share price is twice as high as the initial share price. We are at T0, so we don't know whether the share price after 1 year will be twice as bigger than the initial price. And I pay you 0 if ST is not as twice as big as the initial price. Okay, that's the payment at T, that's the payoff at T. And the question is how much should we pay at T equal to 0 for such a contract? Okay, and Gersonov theorem gives me the power. It says, just calculate one expected value, and we are done. Okay, X0, the value of this contract at time 0, we can calculate as expected value star of discounted future value for all T. But for T equal to 1, I know the price. I know the payoff at T equal to 1. They are given. The payoff at T equal to 1 are given. So I will say X0 is expected value star exponent of minus R times 1 times X1. Okay, but what is X1? X1 is clearly equal to $1 if S1 is twice as bigger than S0, and is 0 if S1 does not satisfy this condition. Okay, that's great. We just need to calculate one expected value. What is the expected value of this random variable? This random variable has only two values, 1 and 0. How to calculate the expected value of such a random variable? We may take constant outside the expected value, so it will be exponent minus r times expected value of x1. How to calculate expected value of x1 if x1 has only two values? What shall we do? That's an easy question. If you have a random variable that takes two values, how you calculate the expected value of this random variable? Anyone? How to calculate the expected value of a random variable that has two values, 1 and 0?
It will be probability is 1 greater than 2.
Yes, yes, exactly. You are right. We just calculate, but not probability, probability star, yeah? Because we have expected value star, we need to use this strange probability, the existence, this probability is asserted by Gersanov theorem. So we need to use strange probability. Okay, but we just calculate this strange probability. Well, what the problem? Okay, this is exponent minus r p star s1. What is s1? S1 is exponent of what? Of sigma times w. I just copy the expression for s1. Yeah, let's go back and see the expression. This is the expression for s1. Okay, that is the expression for st. Yeah. I will just plug in t equal to 1. My contract expires after 1 year. So I will get here x as 0 times exponent of mu times exponent of w1, sigma w1 minus 1 over 2, sigma squared over 2, bigger than twice as 0. Okay, as 0 will cancel out. I will get expected value of minus r. I will take log. Yeah, I take logarithm. So it will be mu plus sigma w1 minus sigma squared over 2 is bigger than logarithm of 2. Just I cancel s0 and I take log. Yeah, I take log from both sides. And now I see the problem. P star W1 and R is not normally distributed. Yeah, that's the problem. Because W1 has normal 0, 1 distribution on the probability measure P. And we have changed probability measure, yeah, because according to P, we can't calculate the expected value so easily because MT is not a martingale and we have changed probability measure. It seems that we are stuck because, WT is not a winner process anymore because we use probability measure P star. So once again, WT is a winner process under probability measure P, and WT star is probability measure is a winner process under probability measure P star. Yeah. Hence, oops, we have a problem. But we have a brave Gersanov who says, "But we know how to go back." Yeah. The brave Gersanov says, "Oh, that's easy. You can easily replace WT by WT star." So I use the formula from Girsanov theorem, and it says that W1 star is W1 plus mu minus R over sigma times 1. Hence, W1 is just W1 star minus mu minus R over sigma. And I will plug in this value of W1. And I will calculate the probability. Yeah, what will I have? I will continue on the next page. It seems like some black magic. We introduce new probability measure, everything is a martingale, and we easily calculate x0. And x0 is a real variable, yeah? It has a real meaning, that's the current price of a financial claim. P star mu plus sigma times W1 star minus mu minus R over sigma minus sigma squared over 2 is bigger than log 2. Exponent of minus R. I collect everything. So I just open the brackets. I will see that mu will disappear. Yeah, I open the brackets. I will see that mu and this will disappear. Yeah, sigma times sigma will cancel out. I will divide what will I have? Sigma W1 star. Sigma W1 star is bigger than log 2 plus sigma squared over 2. What I have more? I have, I think, minus R, yeah? Or I have exponent minus R times probability star that sigma 1 star is bigger than log 2 plus sigma squared over 2 minus R over sigma. But now I see that I have everything I need to know. I don't need explicit construction of this probability measure P star. I don't need the explicit link between P star and P given by Redon-Nikodym derivative. I just need, all I need to know is that W1 star has on the P star, it has normal 0-1 distribution. That's all I need to know. And hence, this is the probability that a standard normal distribution is bigger than this value. And I don't care about the rest, how they are, what are the explicit expression for P star, I don't need it. I just say that is exponent of minus R times 1 minus f of logarithm 2 plus sigma squared over 2 minus R over sigma. And this f is a standard normal CDF. Yeah, it is tabulated. You can use tables, or you can use computer to calculate this value. And hence we have solved our first problem. We have priced the derivative without partial differential equations. There is another way. Piotr will show you the way through partial differential equations, but this magic way through Girsanov theorem avoids partial differential equations. There is another way to solve this problem, this type of problems, not this particular problem, this type of problem. But okay, we have the answer. So the question was at time t equal to 1, we receive $1 if S1 is twice as bigger than S0. What is the price of these financial claim. Yeah, we have a payoff in the future. What is the current price? What is the current price of this contract? So how much should I pay if someone credibly says, oh, I will pay you $1 if S1 is very big compared to S0? And the answer, okay, we should pay, or we should pay for this promise if we believe the promise, obviously, yeah. If we believe in the promise, we should pay exponent minus r times 1 minus f of logarithm 2 plus sigma squared over 2 minus r over sigma. And we have a very magic way to do this. And basically, next time we will solve more problems of this type. But next time we will start from we will see that it's very quick. It's very we may calculate that very quickly if we start from here. Start here. To calculate the current price, you need to calculate expected value star, and just just look at the contract. So whether the price of the contract at time equal to 1, or maybe the price of the contract is easily seen at some moment of time. Yeah, it's easy to understand that if the contract pays you $1 at time moment 1 under some conditions, that this contract is worth $1 under these conditions at time moment 1. So it's easy to calculate the price of this contract at time moment 1. If you are alive at time moment 1, if you see that the condition is satisfied, you should pay $1. Or if it's not satisfied, you should pay $0 for this promise. And hence we just calculate expected value. Oops, we are done. We need to do the trick. We need to go from WT that is in the, we need to do a trick. We need to go from WT that is postulated in the Black-Scholes model. We need to change to this WT star, but the answer is correct. We just obtain x0. X0 is real observable random variable. That's the current price of this contract. Okay, I think we are done. We have calculated the price of a financial claim using Gersonov theorem. We will consider more examples next time, but I think that's a great achievement. We are brave as Gersonov. That's all. If you have any questions, don't be shy.
Okay. Bye. No questions from me.
Okay. See you next time. Bye-bye.